Thank you for joining me in this configuration section of the video Inter-AS MPLS VPN option C. The focus of this section is on the configuration guide, which includes the steps that need to be taken when configuring the devices that participate in this solution. The aim of this video is to establish connectivity between remote 2 and remote 3 over the Inter-AS links that are indicated in this design. We would see how the peering between the route reflectors will extend the connectivity, and here the configuration that is existing on router 9 as shown. Here we already have the Inter-AS link between R9 and R5 already established, and we have IP connectivity, which is also shown here. As you can see, the IP address is operating in the /31 in order to conserve IP, and because this is just a point-to-point link, and also reachability is established between them. Here also we have the BGP peering established to R11, which is the route reflector in this case, and at the moment we do not have any route that represents the loopback of router 6, which is the remote route reflector. So the configuration of the BGP4 is to be done on R9 being the ASBR towards R5, and that is simply by configuring the basic BGP implementation. And remember, we also need to enable the exchange of labels using the send label command in order to activate that neighbor to be able to send prefixes that are labeled. And the prefix list in this case is actually meant to filter down on the prefixes that will be exchanged between these ASBRs. In this case, we are only allowing R9 to advertise this prefix that is the loopback address of the route reflector in the local AS. In this case, R11's loopback address is what we have specified in the prefix list. This prefix list then is called upon in a route map that will be attached to the redistributions that will be done. In my previous video, you will remember also where I stated in the configuration guides that you need to filter when you are doing the redistribution so as to prevent unintended routing loops and other issues that may cause suboptimal routing. Now we have to redistribute the IGP into the BGP. This is to establish connectivity between the loopback addresses of the route reflectors. And that is the essence of having this route map called in the redistribution process with a metric. The metric in this case is also for traffic engineering in order to specify which is going to be primary or which will be secondary. In the same vein, you have to also distribute the locally connected Inter-AS links. And this is to achieve the BGP requirement of reachability to the next stop address in order for a prefix that is learned from the next stop to be marked or flagged reachable. Hence, it is important for R9 to redistribute the local Inter-AS into the local IGP for internal routes to be able to reach through to the other side when they send their traffic over it. Now, we need to verify if we are seeing that, and you would see that 11 seconds old prefix, which is the locally connected Inter-AS link. And back to R9, we can specify the metric in order to influence the way traffic is seen to flow through that network. Now that we have this configuration done, we'll go to the other side of the link, which is R5 being the ASBR of the other AS, and do exact the same thing. You configure BGP and then you do your redistribution, and remember your filtering as well. So this is a mirror configuration that was done on R9. Here we have to enable the send label and this will activate the MPLS BGP forwarding implementation. This is also to allow that interface or the peering to exchange label traffic or label packets or routes, as you may call it. Here the prefix list also is filtering down to only the local route reflectors loopback address to be advertised over this BGP, because that is actually what we need. We don't need any other prefix with respect to this particular design. We only need the loopback of the route reflectors to be exchanged over the inter-AS links. And as soon as this is done, you have to also attach it to the BGP peering and also the redistribution of the IGP into BGP and backwards. Remember also we have to redistribute the locally connected inter-AS link into the IGP. Here we are doing redistribution of the IGP, which is EIGRP in this case, into BGP4 that is running between the ASBRs. And you also have to call on the route map, which is actually advertising only one prefix, and that is local route reflectors loopback address. Thereafter, you need to redistribute locally connected inter-AS link into the IGP. And that's why we have redistribute connected. Then you specify the metric as usual. Then call on the route map to pick only the inter-AS link that needs to be redistributed into IGP. Now you can go to R6 to check if there is any new route that is being learned. In this case, we are checking out for the loopback of the remote, and it is learned via BGP. This is not desired. Remember, we don't need to learn the loopback addresses of the route reflectors by BGP. Reason is because we need to extend labeled session, that's LDP session, across the inter-AS links. And in that case, it means we have to filter and ensure that the IGP is the source of the loopback address. And you see here also the same thing is happening. BGP is better off learning that particular prefix, which is undesired. Right now, what we need to do is to filter that out of BGP and enforce the IGP as the primary source of the loopback address of the route reflector. So the prefix list here is denying or dropping the loopback address of the remote route reflector, but allowing every other thing to pass through in BGP. It means once BGP learns that particular prefix over the inter-AS link, it will filter it out and allow other prefixes that are learned to pass through. Now we have advertised it to the other side, so you can see that it is not learning the loopback of the other end by BGP anymore. It is only limited, and ASBR is no longer advertising it to the route reflector, which is okay. The ASBR can learn and keep the route to itself and not sending it to the route reflector, because the route reflector only needs to learn the loopback of the remote route reflector by IGP. And that is why we have to redistribute BGP4 into the local IGP. And also you would see up there that we already have the prefix of the loopback for the remote AS in BGP table, but we need it to be redistributed into local IGP so that our local route reflector, in this case R11, be able to learn that particular prefix by IGP. I omitted the level running ISIS. In this case, it's the L1, L2. So take some time to definitely propagate it. There is really nothing much to do here. We have already specified. I think I'm not missing anything. So let's check again. Let's check what we have on the other side again on R11. And there it is, 23 seconds old. You will find that already in the routing table, which means we are fine for this side, and we can replicate same on the other end of this link. Remember, we have to write a route filter of any choice of yours. I'm using prefix list in this case in order to pick on that particular prefix. I don't want it to be learned by BGP, and that is why I have to filter it out. In this case, we have to drop it so that R5 will not advertise it to R6, which is our route reflector. And then we allow all other prefixes to pass through. Once you have this configured, you can then apply it to your BGP session between R5 and R6 in the outbound direction, because the traffic or the prefix is being learned from one AS and will be advertised out. So that's why I'm using the out direction. Now we can check to see that it's not in the table anymore. The next thing to do is then to redistribute the BGP into the IGP. As we see here, both prefixes are there in the BGP table, but we want it to be extended to the route reflector via the IGP as the source protocol. And that is the essence of this redistribution of the BGP4 into IGP, which in this case is EIGRP. Now we can see that the route is being learned only 2 seconds ago by EIGRP, and this says reachability is expected. When you source it from the loopback address, you would see the way they're going, and in order to also confirm if it is going through the right path, you can use the traceroute utility or diagnostic tool. So we expect that the traffic should go through 9 to 5 and then to 6 when you source it from R11's loopback address. And once we have this establishment of that connectivity, it means that we can proceed to the configuration of the route reflector pairing. The route reflector pairing requires you to establish the BGP session, but before then, let me show you the trace route so we'll see how many hops away, because we also need to specify the eBGP multi-hop. eBGP multi-hop is very important when configuring this particular device. The route reflector requires you to specify, and in this case our hops are 3 away, but because it's a loopback you add 1 more to it, which means you have to specify eBGP multi-hop number 4. You are setting our source to loopback and also the multi-hop to number 4. You activate VPN address, which is actually the MP-BGP, and this is where it matters because you will be using the route reflector to exchange MP-BGP prefixes, that is labeled prefixes, and that's why you have to do that. Then the reverse also, which is the mirror configuration on the remote side, is the same approach. You specify your update source to be loopback and also specify your eBGP multi-hop as well to be 4 in this case. Now note, in a situation where you have different paths that could lead to the loopback addresses, you need to be sure that the update source is fine and the multi-hop value, in case there is one hop longer for an alternate path. If the primary path should fail, then there is a problem because it will not form because of that discrepancy in the multi-hop value. So now we are done with this, and we can see that control plane wise we are learning the prefixes of the remote AS. And remember also that we need to disable the ARF, that's automatic route filter, but we will get to that in a couple of minutes, probably seconds. So here is just verification, and we can see that we are actually learning those prefixes that are coming from the other end. But there is a problem. It is gone back to learning the loopback via BGP, which is directly between the route reflector, and this alone could cause the session to continuously flap because it's learning its peer's IP by BGP, which will create a continuous instability of the BGP session. And that is the essence of filtering the routes that are received by BGP. You have to deny receiving its own loopback IP address by BGP, because now it looks as if you have a loop where R11 is learning about the loopback of R6. Let me take that again. When you're configuring BGP between two devices, always prevent them from learning the peering addresses via BGP, which is set up directly between them. The reason is because it will continue to make the session flap. So please take note. And so we have ensured that the session directly between the route reflectors will not advertise the loopback addresses which they are pairing with. Hence, we have to drop it and then move on. Right now, I've disabled the ARF on R11, and we will do the same on R6 as well. We also have to do the filter in order to drop the sessions in between them. Now that we have seen the session reset, we have to apply a filter to ensure that this particular prefix will not be sent over the BGP directly to the route reflector on the other side. Note, IGP should always be the preferred source protocol to learn about the remote route reflector's loopback address in order to allow the LDP or label exchange to go end to end across the ASs. And the same thing is happening here. You apply in the outwards or outbound direction to ensure that it doesn't go there. It doesn't get advertised to the other side. As soon as this is done, you can verify again, and then we can move on to the next phase. So we are back and we are learning those prefixes. And in this case, we can see that the loopback is learned by IGP, which in this case is the EIGRP. Also, if you check the LFIB, that's the Label Forwarding Information Base table, you can see we have the labels exchanged. That's because IGP is our source and it's able to extend the LDP sessions. Now let's compare something. Let's imagine that we did not use the IGP as our source protocol for those loopback, and we will compare what the LFIB table looks like. So I'm taking it back just for you to see the difference and the importance of doing this filtering to ensure IGP only is the source. We have to just refresh very quickly. And now let's see what our LFIB looks like. Now, did you see that? It will drop it because it is learning it by BGP, and there is no label that is actually going out for this prefix. And if you check this prefix, it's coming by BGP. So it's important for you to filter it out so that IGP is preferred over the BGP. Similarly, on this R6, you'll find out it's the same image that you have, the same kind of appearance, because BGP is actually learning about the loopback of the remote route reflector. That is the importance of using IGP in order to extend the labels across the AS, and so always note to consider that filtering when you are deploying or implementing this solution. Now we move to the next phase, which is the remote side. How are they learning? Right now, they are not learning any prefixes because we still need to do a configuration on the PE side. On R8, we can see there is nothing coming from the PE. And the same thing on R12, which is at remote 2. The PE needs to be configured because we need a specific VRF to be advertised. But before then, it needs to be imported into the local VRF table. And here I'm showing you what we have, both VRFs, but it is yet to be advertised to the remote because we need to import them into the local VRF before the advertisement can be successful. And as you see here, that's our RD for the interesting VRF. And we just have to import it into the local VRF on this PE. R11 in this case is acting as the PE to R12 and also the route reflector for the AS. And now we are learning three prefixes from R11. As you see that, we can see these three prefixes. R11 now is advertising the 3 to R12, and there they are. You can see them coming from 54.11.12.0 and the AS number where they originated from. In the same vein, we have to replicate on R7 so that R8 will be able to learn those prefixes. Our RD in this case is 54230. That is actually the one that we are targeting, and it needs to be imported into the local VRF on R7 towards R8. After then, we will see the number of prefixes that should appear in the table of R8. So we go to R7, check the existing VRF config, and then import the interesting RD. Right now, we don't have it yet. It's not learning. Then, as soon as we apply it, then we can see that it's learning the 4 prefixes already. And these are the 4 prefixes coming from 78.0.0.1. And you can see the source of those prefixes, 64717. That's actually the one that is the AS where they came from. Now we can verify using our trace tool. Remember to specify your source in order to get the appropriate response. So here we are seeing the path through which the traffic is flowing between the remote is going through 95.0.0.0, which is a prefix between R9 and R5. And the same thing when you do a trace route backwards from R12 towards R8, sourcing it from the loopback or one of the LAN IPs behind R12, you can see it's going through 95.0.0.1. That is exactly what we have, and with respect to this HAME, we have established that connectivity between the remotes. However, you would see that 95 seemed to be a longer path. Well, before I show you that, let's see the LFIB and see what is going on. The LFIB on R11 here for the loopback is showing us the preferred path, which is through Fast Ethernet 1/1. The same thing with the BGP table. This, in this case, is the MP-BGP table, which is like the global single MP-BGP table that takes care of all VRF prefixes coming from all those sides. And we can see it is the one that is actually reflecting in the LFIB table. And loopback is learned by IGP. That's all this part, what this part is showing. So looking at the shortest path, you will agree with me that R10 and R7 are the shortest path between the remote. So I will activate the link between them to see how traffic should flow normally between remote 2 and remote 3. Now you see it is shorter by 2 hops, as you see in this case. It's going through R11 to R10 to R7 and then to R8 and backwards as well. So this path between R10 and R7 is the shortest path. But the interesting part is that the session between the route reflector is always going to be there to pick on the underlying path to which that traffic should flow. And so the establishment of this connectivity is protected, because if you have any failure on the primary path, which is between R10 and R7, you already have the backup path, which is between R9 and R5. And this kind of service is resilient and also protected and ultimately scalable. This is one thing that needs to be considered when selecting which approach or which of the options of the inter-AS MPLS VPN is to be considered. If we run a test, just like I'm showing you now, to see how the failover will be, or the switchover as you may call it, you would find out it saves a lot of resources in terms of financial resources for companies when they have backup appropriately set up and business is protected from single point of failure. Mind you, the speed at which the traffic is switched over also matters, and this can be factors of different high availability considerations. That's exactly what is showing there, that we are now going through the other path, which is through R9 and R5, and this already shows you that a single point of failure cannot isolate the remote site from reaching the rest of the enterprise global network, or in this case it is the remote site too. You can also verify what the LFIB looks like. And you see for the prefix, particularly concerning the secondary path, you are seeing that it is learning it by the other interface. As you see, we have the connectivity fully established. Now I'm activating the primary path again so that we can have the proper flow through the shortest path. And here you don't see any kind of timeout because it is taking over to the primary path. So here you can see the trace route is gone back again to the primary path through 107, which is the link between R10 and R7 respectively. Similar thing is happening here through R10 and R7. That is exactly how it is. That is actually what happens when you consider using option C. You have to do a lot of filtering to ensure that only the desired loopback IP addresses and probably some other addresses that you want to monitor or to extend connectivity to are allowed to go through the BGP, the IGP, and also during your redistribution. Importantly, please note that the loopback address of the route reflectors are to be learned only through the IGPs so that LDP session and label exchanges can easily happen. And that is what is very, very important. And as I said earlier, according to considerations with respect to security concerns, this option might not be suitable when you consider two different ISPs that are under different administrative systems or control. And so you might not see this happening between two ISPs in the real world, except they have something very unique that they need from this particular deployment. Note, this kind of design can be dedicated to a particular service across different regions for an enterprise, which is something they could consider, especially if the enterprise is in control of all the ASs across the regions. In conclusion, here are the list of the inter-AS MPLS VPN option C attributes. And here you will see on the list that this method is the least secure but the most scalable among all the options of inter-AS MPLS VPN. It leverages on the scalability benefits of BGP route reflection in large networks. It is important to note that you can use this option when you are considering a scenario of acquisition or merger between two service providers, and that is talking about two ASs that will operate under the same administrative authority. This is not to say that it cannot be used for scenarios where you have different ASs, but like I have stated earlier, even in the configuration section, that it poses security concerns to each of the networks that you might be considering. And so you might not really see this deployed between two ASs in real life scenario, except in cases where they have something like a unique service they have to share together or probably extend across networks or regions. Then this would actually be a good option. But then it's not so mandatory to stick to option C, because there are other options that can fetch the extension that you want to do. Remember that the design option is subject to business goal among other design factors. And here you have one glance that captures the full story of an enterprise that is using the three options to connect to different locations, as you can see. So feel free to share this video and other videos I have done. You will find them in the description section here, and you can send a question or drop your comments in the comment sections. I will be happy to respond to you. I would like to thank you for viewing, and I hope you have enjoyed it. Until I come your way again, stay safe.